Bismillahirrahmanirrahim. Assalamu alaikum. Our today's lecture is about combinational logic circuits. In today's lecture, we are going to discuss design procedure of different combinational logic circuits, including adders, subtractors, multiplexer, demultiplexer, encoders, and decoders. Combinational logic. What is a combinational logic? A combinational logic circuit consists of logic gates. The circuit operates with binary values. The output of combinational circuit depends on the combination of present inputs. The following figure shows the block diagram of a combinational logic circuit. So, a combinational logic circuit, there is n inputs and m outputs. These outputs depend upon the present states of these inputs. To find outputs in any instance, we look to these input variables, the state of these input variables, and their states determines the outputs. In sequential logic circuit, the input state and the output states, the present input state and present output state determines the next state, while in combinational logic circuit only the inputs present at any instance of time determines the outputs. This combination circuit has n input variables and m outputs. Each combination of input variable will affect the outputs. Each combination of this input will affect the outputs. Design procedure of combination circuit. So combination circuits are used to implement real world problems in digital circuits. So what is the procedure? So the first step, find the required number of input variables and outputs. Inputs, how many input will be there and how many output will be there for a given specification by analyzing the real world problem. Explore how inputs. The second step is what we have to do, we explore the relationship between inputs and outputs, how input and outputs are related, and we develop a truth table for that. Once we find a relation between inputs and outputs, how inputs and outputs are related, so then we develop a truth table. If there are n input variable, there will be 2 raised to the power n possible combinations. If for 2 inputs, we will have 4 possible combinations. For each combination of input, find the output values. The third step is find the Boolean expression for each output. Suppose if we have 2 outputs, then we have to find 2 Boolean expression for 2 Boolean expression. If we have 3 outputs, then we have to find 3 output expression in terms of input variables. If necessary, then the fifth step is simplification. If necessary, simplify these expressions. The last step is implement Boolean expressions corresponding to each output by using logic gates, and, or, not, NAND, NOR. So using exclusive or exclusive NOR, using these gates, we implement the Boolean expression. The first combinational logic circuit is binary adder. Adder is obvious from the name. Binary adder adds 2 n-bit numbers. Combinational logic circuit which performs the addition of 2 binary numbers is known as a binary adder. Combinational logic circuit which performs the addition of 2 binary numbers is known as binary adder. Types of adder are half adder adds half adder adds 2 single bit binary numbers, single bit numbers. A full adder is 2 single bit binary number and an input carry, so it's a 3-bit adder. 3 single bit number, it adds 3 single bit numbers. 2 are the number bits and third bit is the input carry. Binary parallel adder adds two in-bit numbers. Binary parallel adder adds two in-bit binary numbers. We have 2-bit numbers, 3-bit numbers, 4-bit numbers. So this is a binary adder. Half adder. So the first step in design procedure, we must know how many inputs and how many outputs are there. So an half adder adds two single bit binary number. So two single bit numbers. So number of inputs is equal to 2 because it adds two single bits. So one bit represent one input, the other bit represent the other input. So we have two inputs by definition of the half adder. Number of outputs. How to find a number of outputs? So let's add these two bits. So the two bits can be 0, 0. So 0 plus 0 is 0. 0 plus can be 0 and 1. So 0 plus 1 is 1. And 1 can be 1 and 0. So 1 plus 0 is 1 and can be 1 plus 1. So when we add 1 plus 1, we get 1 0. So we get 2-bit result. So the output is 2-bit. This one represent, this is the carry and this is the sum bit. So in these three cases, the carry bit is 0. So half adder, in half adder we have two outputs. One is the sum output and the other is the carry output. So we have two outputs. In the last rule we have 2 bits in which 0 is the sum bit and 1 is the carry bit. In the first three cases the carry bit is 0. Therefore the number of outputs of a half adder is 2, sum and carry. The half adder has 2 inputs and 2 outputs. Some outputs are one output is designated as sum and the other is designated as carry. So for 2 input combination, now we are going to develop a truth table. So for 2 we have 2 inputs. So for 2 we have to list 4 possible combinations. So list this input. First list this input combination. So we have these 4 possible combination. Both bits can be 0 0. Both one bit can be 0 and the other be 1. So these are the 4 possible combination for 2 inputs. The one input is designated as A, the second input is designated as B. So look, this is a block diagram. So in the block diagram, these are the inputs A, B. We have 2 inputs and we have 2 outputs, sum and carry. No, to travel, so we have 4 possible combinations. So the sum output. So when we add these 2 bits, 0 plus 0, so the sum is 0, the carry is 0. When we add 0 and 1, so 0 plus 1, the sum is 1 and the carry is 0. So we develop these outputs. 1 by using the rules. 1 plus 0, so the sum is 1 and the carry is 0. 1 plus 1, the sum is 0 and the carry is 1. So this is the table. So the third step, develop the third step this is the first step to find number of inputs and output. This is the second step to develop a truth table, and the third step is find Boolean expressions for the output. So we have 2 outputs, so we will have 2 output expressions. One is S and the other is carry. So as if we S, so the sum is 1 over here and 1 over here. So in SOP expression, make a product term of these input variables. So A is 0, so A bar B, and for this the product term is A and B is 0, so B bar. So A bar A, B bar plus A bar B. And look, this pattern, whenever you see this pattern, A, B bar plus A bar B, so this represent an exclusive OR operation. So it can be represented by this symbol. This is the symbol of exclusive OR. So A exclusive OR B. And for C, we have in the output column we have only 1. So SOP expression will contain one product term, one main term. So the main term is A, B. Both variables are 1 for this combination. So we have C. So this is the carry. Now to implement, so A S is equal to A exclusive OR B. So A B. So that this is the logic circuit. So A exclusive OR B. So we put an exclusive OR gate. So this is the sum, and this is the carry. So for carry, this is an AND gate. So A is taken from this point, so and B is taken from this point. So this is A B. So the output C is equal to AB, and this is A exclusive or B. So this is the logic circuit for half adder. This is the logic circuit for half adder. So this is with a design procedure. This is first step, find number of input and output, and draw a block diagram. The second step, develop a truth table. Number of inputs are determined, so how many inputs are there. So we will have 2 raised to power n possible combinations, and using rules, some analysis, develop outputs, and then Boolean expressions. This is the third step. In the fourth step, draw the logic circuit. So this is the logic circuit. So if A is 1, B is 0, suppose, so this is exclusive OR gate, the sum will be 1. If the inputs are different of exclusive OR, the output will be 1. If the inputs are the same, the output will be 0. So for 1, 0, we will get S equal to 1, and 1 and 0, and carry will be 0 because B is 0. So when this is 0 and this is 1, so the output will be 0. So this is the block diagram, sorry, it's a logic circuit for half adder. This is the logic diagram for half adder. Full adder. A full adder adds 2 single bit binary numbers and an input carry. So the total number of inputs here is 3. From definition, it is always stated the number of input is 3. 2 single bit numbers plus an input carry. Number of outputs, when we add 3 bits, we get a sum bit and a carry bit. So therefore, the number of outputs is 2, sum and carry. So, and this we have 2 carries. One is input carry, so it is designated at CI, input carry, and CO. This is this symbol, this letter is used to represent output carry. This is the block diagram. So A, B, we have the 2 inputs. So and the third input is, this is input carry, and we have 2 outputs, sum and the carry out. So now we have 3 inputs. So we have 2 raised to power 8 possible combination to develop truth table. So we are going to develop a truth table. So these are the inputs A, B, and CI. So we have these 8 possible combination for these 3 inputs, and these are the 2 outputs, sum and carry out. So now to develop this sum and carry values, so we add these 3 bits. So 0 plus 0 is 0, and 0 plus 0 is 0. So the sum is 0, the carry is 0. So 0 plus 0 plus 1. So sum is 1, carry is 1. So we using rules of binary addition, we develop this truth table. From this truth table, the third step is Boolean expression. So develop a Boolean expression. So this is the Boolean expression in sum of product. In sum of product, again we take ones in the output columns and form a product term for each one in the output column, and we sum all the product terms. So for this one, we have A0, so A bar, B bar, and CI. This is 1, so it will contain no bar. So this is the first product term. For this one we get this product term, and for this one we get this product term, and for the last one we get this product term. So this is a little manipulation of the sum output. This is a little manipulation of the sum output. So look, if we take this term, and we take this term. So look, A bar in these 2 terms, this term and this term. So A bar is common. So take A bar. So we will left with B bar CI plus B I. And in these 2 we have A is common. So B bar and CI bar, and BC. So A is common from these 2. So this is A bar. So look, this is an exclusive OR gate, and this is an exclusive NOR function. When you look this pattern, this is an exclusive OR, and this pattern represent exclusive NOR. They are the complement of each other. So exclusive NOR is the complement of exclusive OR. So this is exclusive OR, and we take exclusive NOR and complement of that exclusive OR, so we get exclusive NOR. So A bar, and this is what it's B CI, and this is B CI exclusive OR CI whole bar represent exclusive NOR gate. So we can use the properties of exclusive OR gate, so we get A exclusive OR B exclusive OR CI. So this is what the sum function. The sum function is manipulated in exclusive OR gates. The carry out function, so in carry out we have 4 ones, so we will have 4 product terms. So the product terms of this is A bar B CI, and the product term, so A bar B CI, and this is the product term of this one is A B bar CI. So if we manipulate this, we get by taking common, so CI in these two terms we have CI common, so we will left with this. This is A exclusive or B, and in this we have CI plus bar plus CI. So using rules of Boolean algebra, this is equal to 1, so we will left with this. So this is the simplified Boolean expression for sum output, and this is the simplified Boolean expression for carry out. Now we are going to implement. So this is the implementation. So this is the sum, and this is the carry. So look, the sum A B, so A exclusive or B, and CI is exclusive OR with B. So this is the CI, and this is the second exclusive OR. This A exclusive OR B is represented by this exclusive OR gate, and output of this exclusive OR gate is exclusively ORed with CI. So this is the sum, and this is the carry out. So CI AB, so we have AB, so this is AB. So this term is implemented by this AND gate, and this is implemented by this AND gate. This is the output of exclusive OR gate, the first exclusive OR gate, and CI is ANDed with it. So we left and these two. This is a sum. So we for this plus we use OR gate. So this is the output. Look why it is called full adder. So look, this is an half adder, and this is an half adder. So when we combine two halves, so we get full. So when when two half adder are combined, so we get a full adder. So this is why we call it a full adder, when we get 2 bits with an input carry. So this is the implementation. This is the implementation of full adder. A binary parallel adder. A binary parallel adder adds 2 in-bits numbers. An in-bit binary adder requires n numbers of full adders connected in cascade. Suppose look at this example. So we have 2 numbers A and B. A is an n-bit number and B is an n-bit number. So these 2 are n-bit numbers. So at the first stage we add these 2 bits. So look, this is an half adder. When we add 2 bits, so it generates a sum and a carry. A carry is moved to the next column. This is what, no, it becomes a full adder because we add 3 bits. This is an input carry for the next stage, and these are the 2 number bits. So A1 B1. So we got C1 and S1 here. So it is moved to the next stage. The carry is moved to the next stage. So again we have this full adder. We can use for the first stage an half adder because it has 2 inputs, or we can use a full adder with carry in equal to 0. So we can implement this. The binary adder is also called as a ripple carry binary adder because the carry ripples from one stage to the next stage. So we generate a carry is generated from this, and it is moved to here, then move to the next stage, then move to the next stage. So that's why it is called a ripple carry adder. A 4-bit binary adder. A 4-bit binary adder adds. This is an example of binary adder. So the 4-bit binary adder performs the addition of two 4-bit numbers. So this is a 4-bit number, this is A is a 4-bit number, B is a 4-bit number, and this is the sum when we add. So the first in the first case we have carry 0. So this is a first full adder, this is the second full adder, this is the third full adder, so this is a full adder. So A naught, B naught is added over here with C naught equal to 0. So in first case Cn is equal to 0. So this is the first Cn. No, the C out of this this adder is the Cn is connected to the Cn LAN of this second full adder. So they are connected and cascaded. So this adder acts as a 4-bit binary adder. It adds two 4-bit numbers. To develop an 8-bit binary adder, so add 4 more adders stages over here and connect this C4 to the next the carry in of the next full header. So in this way parallel adder is implemented. Binary subtractor. The circuit which performs the subtraction of two binary numbers is known as binary subtractor. We have a half subtractor performs subtraction of two single bit numbers, and full subtractor performs subtraction of two single bit number with an input borrow. Here we have a borrow. In adder we have a carry. This is the design. Half adder half subtractor subtracts 2 bits, computes subtraction of 2 bits. So we have 2 inputs and we have 2 outputs, a difference bit and a borrow. So this is a half subtractor. The truth table is we have 2 inputs, so we have 4 possible combinations. So again the difference bit is 0 minus 0 is 0, 0 minus 1, the difference is 1 with borrow 1. 1 minus 0, so the difference is 1 and the borrow is 0, and 1 minus 1, the difference is 0 and the borrow is 0. So look, the D output and the S output in adder, half adder, we have the same bits. They are the same. So the Boolean expression for D, A exclusive or B, and for B naught, we have this is B naught, A bar, B. So what it means, a borrow is taken over here. So this is the implementation. So A and B, these are the inputs. This is exclusive OR gate, and this is the difference bit. So we implement this function as the exclusive OR gate, and we can implement this function A. So A is taken from here, and inverter is placed in the path. So this is here we have A bar, and the output B. So this is B, the second bit, and it. So we have implemented this with this gate. So this is what the difference bit, and this is the borrow bit. So these are the 2 outputs. This is the implementation of half subtractor. A full subtractor have 3 inputs, A, B, and BI, call it, we have B, so that's why it's CI. This is the input borrow and this is the output borrow. So we have 3 inputs, so we have 8 possible combinations, and these are the outputs generated, and these are the expressions. So the expression of D is the same as that of the full adder, and B naught there is a little difference. So in B naught borrow output, if we compare it with the carry out in full adder, so this is complemented and this is complemented. So to implement this, we have C, we have A, B, and C, and A is complemented. So A bar, this is A bar B, and this is A exclusive or B complement. So and this is C. So they are ANDed, and the output is OR. So this is what the implementation of full subtractor. Parallel binary subtractor. The circuit which performs the subtraction of 2 n-bit numbers is known as parallel binary subtractor. We can implement a parallel binary subtractor in the following 2 methods. Cascade full subtractor, just we have done in full adder, are 2's complement method. A minus B, in 2's complement we have performed 2's complement subtraction, so A minus B is equal to A plus 2's complement of B, and it's equal to A plus 1's complement of B plus 1. So we can use, how do we take 2's complement? Take 1's complement and add 1. So this is, this plus 1 means okay, we are computing 2's complement. In practical circuit like LU, binary subtraction is repeated using 2's complement method. So we will discuss this method. 4-bit binary subtractor. A 4-bit binary subtractor is similar to that of 4-bit binary adder. We can transform adder into subtractor by complement the bits of B, subtract. Complement the bits of B by using inverters, 1's complement, and assign an initial carry 1 C0 equal to 1 to convert 1's complement into 2's complement. So look at this table. So this is a 4-bit number. We have another number B. So this is the 1's complement of B, B0 bar, B1 bar, B2 bar, B3, and initial carry C0 is made 1. So for 2's complement of B, to compute 2's complement of B, and add. So when they are added, so we get S0, S1, S2, S3, and C4. So the sum is equal to the sum of this and the 2's complement, this and this one, equal to A minus B. So we get this. If C4, if this the last carry is 1, discard it. In case of if this is 1, we discard it. If C4 is 0, then the difference is in 2's complement form. So take 2's complement of this difference, these four bits, and put a negative sign or place a negative sign in front. So this is a, so how to implement? So look, B0 is assigned through an inverter, is given to the full adder through inverter, and C0, the first carry in is equal to 1 to make 2's complement. This generate 1's complement and we add 1, so it generates 2's complement. So that's why it is 1. And this is, look, this is a full adder with a little modification. We have transform it into a subtractor. Adder subtractor. So a circuit which can perform both addition as well as subtraction. So here look, that is again a full adder, and this is C0, and A0 B0 B0 is provided to the full adder through this exclusive OR gate. So look at the exclusive OR properties. So if we exclusive OR B with 1, so we get B bar. So if C0 is 1, then we will get here B bar, and we will get subtraction. If B exclusive OR 0 is equal to 0, so if we make the initial carry 0, so this will be, the output of this will be B0. Okay, so we will get what? Addition. So using this line, we can use it as if we want to use this circuit as an adder, so we make this line 0, and if we want to use this number, this circuit as a subtractor, so we made C0 1. So C0 is used to make this circuit subtractor or adder. If C0 is 0, the output of the exclusive OR gate will be exclusive OR gates will be B0, B1, B2, B3, and the circuit will act as an adder. If C0 equal to 1, the output of the exclusive OR gates will be B0 bar, B1 bar, B2 bar, and B3 bar, and the circuit will act as a subtractor. So this is what an adder subtractor, binary adder subtractor. So it's all about for adder and subtractors. Thank you very much.